Let me begin calmly by setting aside the dramatic images we usually associate with black holes. No violent explosions, no cosmic monsters, just a simple question. What does it really mean when matter collapses so completely that space itself seems to give up? That question is more subtle than it sounds, and answering it requires patience. Imagine gravity not as a force pulling things inward, but as the quiet reshaping of space and time themselves. Picture an ordinary region of space. Distances behave as expected. Time flows steadily. Now imagine adding mass, not suddenly, slowly. As mass increases, space begins to curve. Clocks tick differently. Paths that once were straight now bend. Nothing strange yet. But at some point, the curvature deepens so much that the idea of a straight path becomes ambiguous. How much curvature can space tolerate before its structure changes entirely? Think about escape. On Earth, if you throw a stone hard enough, it escapes. On the Moon, even easier. Escape is about energy and distance. But what if escape requires infinite energy? Not a lot, not absurdly large, infinite. What kind of place demands that? That is the threshold where a black hole quietly appears. No alarm, just a boundary forming in space-time. This boundary is not a surface you could touch. It has no material substance. It is defined by causality itself. Beyond it, all possible futures point inward. Every path forward in time leads deeper, not outward. That boundary is often called an event horizon. But calling it a horizon already hints at something misleading. Horizons feel distant, like edges. This one can pass right through you without any local signal. Imagine floating toward this boundary. No sudden pull, no warning light. Your instruments behave normally. Physics feels ordinary. That is unsettling. We expect danger to announce itself. But here the danger is global, not local. Only observers far away notice something dramatic. They see you slow down, fade, freeze. But you feel nothing special at that moment. Why would reality allow such disagreement? To understand that, we need to question time. Not clocks, but time itself. In strong gravity, time stretches. The deeper the gravity, the slower time flows relative to distant regions. Near a black hole, the stretching becomes extreme. From far away, your time nearly stops. From your perspective, it does not. Whose time is real? The unsettling answer is that both are. Now, imagine crossing the boundary. From the outside, it never happens. From the inside, it already has. This is not a contradiction. It is a feature of space-time geometry. Once inside, the direction you once called outward no longer exists as an option. Space and time exchange roles in a subtle way. Moving forward in time means moving inward in space. Can you resist time? At the center lies something even more mysterious. The equations point to a singularity, a place where density becomes infinite and known laws fail, but infinities are warning signs. They tell us not that something is infinite, but that our description has broken down. So what truly exists there? A point, a region, or something we have not yet imagined? Here is where the story becomes more surprising. Black holes are not completely black. Quantum effects allow them to emit radiation, slowly, imperceptibly, at first. Over immense spans of time, they lose mass. They evaporate. This means black holes have temperature and entropy. That should make us pause. Entropy is about information. So what information does a black hole contain? Imagine throwing a book into a black hole. The pages, the ink, the meaning. From the outside, it seems lost forever. But physics resists that conclusion. Information as we understand it cannot be bees. So where did it go? Is it hidden inside? Is it smeared on the boundary? Or is our understanding of information incomplete? Consider the horizon again, not as an edge but as a storage device. An unimaginably dense ledger where every detail of what falls in is somehow recorded, not inside the volume, but encoded on the surface. This idea challenges our intuition. We are used to thinking that information fills space, but what if space itself is secondary? What if surfaces are more fundamental than volumes? This leads us to a radical shift in perspective. Perhaps the interior of a black hole is not an independent region at all. Perhaps everything that happens inside can be described entirely by processes on the boundary. That sounds impossible. And yet, when carefully explored, it begins to work. Reality, in this view, is like a hologram. Depth emerges from information stored on a surface. If that is true, then black holes are not exceptions, they are clues. They hint that spacetime itself may be emergent. Not fundamental, but constructed from something deeper, something quantum, something informational. We usually think of space as the stage on which physics happens, but what if the stage is built from the script? Now pause and reflect. A black hole forms when matter collapses beyond a certain limit. But perhaps what truly collapses is our classical intuition. We are forced to abandon the idea that space is continuous and absolute. Instead, we glimpse a world where geometry, information, and quantum mechanics are inseparable. This is not just about extreme objects. It is about the nature of reality. Imagine shrinking a black hole, making it smaller and smaller. Eventually, quantum effects dominate. The horizon fluctuates. The distinction between inside and outside blurs. At that scale, even the concept of a smooth space dissolves. What remains? Bits, relationships, entanglement, the quiet web connecting everything to everything else. And here is the unsettling thought. If black holes encode information on surfaces, and if spacetime emerges from that encoding, then perhaps you and I are also encoded. Our sense of depth, duration, and location may be derived, not fundamental. We feel immersed in space. But immersion may be an illusion created by deeper rules we barely understand. So, when we ask what a black hole really is, we are not asking about an object. We are asking about a limit, a stress test for our theories, a place where gravity, quantum mechanics, and information confront each other, and they do not agree easily. That tension is productive. It points towards something new, something incomplete, something waiting to be understood. And if we follow that tension carefully, we begin to see that the deepest mystery is not what happens inside a black hole, but how the universe manages to let space, time, and information arise at all from rules that do not seem to contain them explicitly, and that realization quietly shifts the question we thought we were asking into something much more unsettling. Because once you accept that black holes are not just regions of collapsed matter, but windows into the structure beneath spacetime itself, you are forced to wonder whether the familiar world around you is as solid and fundamental as it feels, or whether it too is balanced on a hidden boundary where information, geometry, and reality itself are still negotiating their terms. And that thought naturally leads us to ask what it would even mean to look beyond that boundary, or whether the very act of asking already places us inside a framework that is itself emergent, provisional, and far from complete. And once you allow that possibility, the idea of inside and outside becomes less reliable than we usually assume. We picture black holes as containers, holding something hidden within, but containers presuppose space as fundamental. If space itself is emergent, then containment may be the wrong metaphor. Perhaps nothing is truly inside a black hole in the way we imagine. Perhaps inside is just a particular way indium is organized. Let me slow that down. Imagine you have a complex message encoded on a surface. From one perspective, it looks flat. From another, rich structure appears. Depth can emerge from patterns, not from extension. In that sense, falling into a black hole might not be traveling to a new place, but entering a new description of the same underlying information. Is motion always motion through space, or can it be motion through relationship? Now think about entanglement. Two particles share a connection so deep that distance becomes almost irrelevant. Measure one, and the other responds instantly, regardless of separation. This is not a signal. It is a correlation built into the fabric of quantum reality. Entanglement weaves systems together. What if spacetime itself is woven from such threads? What if geometry is just the bookkeeping of entanglement? In that picture, a black hole is not merely a region of strong gravity, it is a dense knot of entanglement. Everything that falls in becomes deeply correlated with everything else inside. The horizon marks not a wall, but a transition in how information is shared. Outside observers describe it one way. Inside descriptions reorganize the same data differently. No information is lost. It is redistributed beyond easy access. This reframes the puzzle of the singularity. Instead of a physical point where everything ends, it may represent the limit of a particular description. When we insist on using spacetime where spacetime no longer applies, the mathematics rebels. The singularity is not telling us that nature is infinite. It is telling us that we are asking the wrong questions with the wrong language. Consider causality. We rely on it to define before and after, cause and effect. But near a black hole, causality bends, light cones tilt, futures narrow. Inside the horizon, the future is not unended. It is directed. That feels disturbing. We associate freedom with choice of future paths, but physics is not obligated to preserve our intuitions. It only preserves consistency. And yet, even here, something subtle happens. From the outside, the black hole seems frozen, slowly evaporating. From the inside, processes unfold normally, until they don't. Two descriptions, both valid, ne'er complete alone. This duality suggests that reality may allow multiple, equally real narratives, each limited by the observer's access to information. Now ask yourself a quieter question. If information is preserved, but inaccessible, is it truly lost? Suppose a message is encoded so thoroughly that no observer can ever reconstruct it. Does that violate any principle or just our expectations? Physics demands consistency, not convenience. A black hole may keep its secrets while still obeying the deepest laws. But there is another twist. As a black hole evaporates, the radiation it emits must carry information. Not in obvious ways, not page by page, but subtly through correlation spread across the entire emission. Early radiation looks random. Late radiation does not. The story is not about individual particles, but about patterns across immense time spans that forces us to think globally. You cannot understand a black hole by watching a moment. You must consider its entire life. Formation, equilibrium, evaporation, the beginning and the end are entangled. The past and the future talk to each other through constraints. Time, which felt so local and immediate, reveals itself as a global structure. Pause here. This is not just a black hole story anymore. It is a lesson about how nature encodes consistency across scales. Local observations never tell the whole truth. They are fragments of a larger tapestry. Black holes exaggerate this fact, making it impossible to ignore. Now, imagine a universe filled with such objects, each one encoding vast amounts of information on its boundary, each one hinting that the true degrees of freedom live on surfaces, not volumes. Suddenly, gravity looks different. Not a fundamental interaction, but a statistical tendency, an emergent force arising from how information organizes itself. In that view, falling toward a black hole is not being pulled by a force. It is sliding toward a more probable configuration. Space curves, because information prefers certain arrangements. Geometry becomes thermodynamic. Motion becomes a response to entropy gradients. These ideas sound abstract, but they unify many puzzles into a single framework. If gravity is emergent, then black holes are not anomalies. They are equilibrium states, maximum entropy objects. They pack information as densely as possible without violating quantum rules. That is why they are so simple from the outside. Mass, charge, spin. Everything else has been thermalized into a featureless horizon. Simplicity here is deceptive. It hides immense complexity beneath. The smooth exterior masks a microscopic storm of quantum interactions. We do not see them directly. We infer them from consistency, from the fact that the laws do not contradict themselves, even when pushed to extremes. Now, return to the experience of falling in. You cross the horizon. Nothing special happens locally. That is essential. If something dramatic occurred, the horizon would be detectable, violating the principle that physics looks the same in free fall. The drama is not in the crossing. It is in the global structure that makes the crossing irreversible. This brings us to a deeply uncomfortable idea. Perhaps there is no single, objective account of what happens. Perhaps different observers require different descriptions that cannot be merged into one picture without contradiction. That does not mean reality is instance. It means our desire for a single narrative may be misplaced. Black holes force humility. They remind us that our intuitions evolved for gentle environments. When pushed into extremes, we must let go of familiar categories. Inside, outside, before, after. Even existence itself may need redefinition. And yet, this is not a story of despair. It is a story of clues. Black holes are not hiding reality from us. They are revealing its structure slowly, reluctantly, through paradoxes that refuse to go away. Each paradox is a signpost, not an error, but an invitation. So when we ask what black holes really are, we are circling something larger. They are laboratories where gravity, quantum mechanics, and information theory intersect. They show us that space-time may be a derived concept, that locality may be approximate, that the universe may be less like a collection of things in space and more like a network of relationships that only sometimes look spatial. If that is true, then the deepest mystery is not what happens at the center of a black hole, but how anything like a center arises at all, how relationships give rise to geometry, how information gives rise to experience. And once that question takes hold, it does not stay confined to black holes. It spreads outward, touching cosmology, quantum theory, and the nature of observation itself, until you realize that studying black holes is really a way of studying the limits of explanation, and that just as the event horizon marks a boundary beyond which certain questions lose meaning, our current theories may be approaching a horizon of their own, where asking what is really happening requires us to rethink what we mean by happening in the first place, because beyond that point, the universe may not be describable in terms of evolving objects in space and time at all, but only in terms of deeper principles from which space-time and even causality are patiently and imperfectly emerging, one relationship at a time. And if that is the case, then the way we usually think about observation itself needs revision. We imagine observers as beings located at points in space, watching events unfold in time. But if space and time are emergent, then observers are not simply sitting inside the universe. They are part of the process by which the universe is defined. Black holes make that possible to ignore. Let me approach this gently. Imagine standing far from a black hole, watching matter fall in. You describe everything using clocks and rulers anchored safely away. Now imagine riding along with that matter. Your description is local, intimate, uneventful. Neither account is privileged. Each is complete within its own limits. But they cannot be combined into a single picture without contradiction. This is not a failure of logic. It is a statement about how information is partitioned. Physics has taught us to accept this kind of complementarity before. Light is a wave in one experiment, a particle in another, not both at once, but both necessary. Black holes extend this lesson to space-time itself. Outside and inside are complementary descriptions. Trying to hold both simultaneously leads to paradox, not because nature is inconsistent, but because we are overreaching. This suggests a new way to think about horizons, not as physical barriers, but as boundaries of description, places where certain questions stop making sense from a given perspective. The horizon does not block matter. It blocks Bunchen transfer in specific directions. It defines who can ask which questions and which answers are accessible. Now consider this carefully. If descriptions are observer-dependent, what remains objective? The answer seems to be relationships, correlations, patterns that persist across descriptions, even when the narratives differ. Black holes challenge us to identify those invariants. what survives every change of perspective. Whatever does may be closer to the foundation of reality. Entropy appears again here, quietly but insistently. The entropy of a black hole is enormous, proportional to the area of its horizon. That is not an accident. Area, not volume. This scaling hints that the true degrees of freedom live on boundaries. It suggests that the universe keeps its accounting on surfaces, even when it presents us with volumes. Think about that implication. If the maximum information in a region is set by its boundary, then stuffing more and more into the interior eventually changes the geometry. The region responds by becoming a black hole. Geometry enforces informational limits. Space is not an unlimited container. It has a capacity, and exceeding it reshapes reality. This turns gravity into a regulator of information density. When too much information accumulates, space-time reorganizes. Collapse is not just about mass. It is about exceeding the informational tolerance of geometry. From this angle, black holes are not exotic accidents. They are inevitable outcomes of trying to pack too much into too little. Now, let your attention drift outward, beyond any single black hole. Consider the universe as a whole. It, too, may have horizons, cosmological horizons that limit what we can see, what can us. These horizons also have entropy, also scale with area. The pattern repeats. Again and again, nature whispers the same clue. Perhaps the universe itself is a kind of information processing system, with horizons acting as interfaces. Black holes then become local expressions of a universal principle. They are where the bookkeeping becomes explicit, unavoidable, visible even to our limited theories. But there is still something unsettling here. If information is preserved globally, but inaccessible locally, then predictability becomes subtle. From your perspective, information falls in and disappears. From a deeper perspective, it is still there, encoded in correlations you cannot measure. This gap between principle and practice is uncomfortable. We like physics to tell us what we can, in principle, observe. Black holes remind us that in principle may depend on the observer. There may be truths that exist, but cannot be assembled by any single observer, not because of technological limits, but because of fundamental structure that forces us to rethink what we mean by explanation. An explanation, traditionally, is something that lets us predict outcomes, but if outcomes depend on global correlations spread across inaccessible regions, then explanation becomes fragmented. Complete understanding may exist only abstractly, not operationally. Black holes push us toward that uncomfortable edge. Now return again to the interior. Suppose, for the sake of argument, that an infalling observer experiences a smooth continuation of space-time, at least for a while. They pass the horizon. They approach regions of extreme curvature. Eventually, classical descriptions fail. What happens then? We do not know, and perhaps we cannot know from the outside. This ignorance is not just technical. It may be principled. The interior description may not be reconstructible from exterior data in a straightforward way. The two descriptions may be related, but not by a simple translation. Instead, they may be dual, like two languages describing the same abstract structure from incompatible viewpoints. If so, then asking what really happens inside is like asking whether a wave or a particle is really the truth about light. The question assumes a single underlying picture, when the lesson may be that no such exists in space-time terms. This is where black holes begin to blur the line between physics and philosophy, though the questions remain grounded in mathematics and consistency. What is reality made of, if not objects evolving in time? What replaces that picture when it fails? One candidate is information itself, not information as stored in computers, but information as a measure of distinguishability, of difference, of structure. In this view, the universe is a vast web of distinctions, and space-time is a convenient, approximate way of organizing them at low energies. Black holes are where that approximation breaks, where distinctions become so compressed that geometry can no longer faithfully represent them. The horizon then acts as a translation layer, mapping microscopic distinctions into macroscopic thermodynamic quantities. Temperature, entropy, radiation. These are not afterthoughts. They are signatures that spacetime is statistical, that it emerges from counting underlying configurations. Black holes are hot because they are coarse-grained descriptions of something far more detailed. Once you accept that, a quiet shift occurs. You stop asking what spacetime is made of and start asking what it is made from. What patterns of information give rise to the illusion of smooth geometry? What rules govern their organization? These questions do not stay confined to extreme gravity. They seep into everyday physics. Even empty space is no longer empty. It is a highly structured quantum state. Black holes simply magnify this fact until it becomes impossible to ignore. And there is another subtle point. If spacetime emerges from entanglement, then changing entanglement changes geometry. That means geometry is dynamic in a deeper sense than curvature. It is responsive to informational rearrangement. Black holes are extreme rearrangements, but smaller echoes may be everywhere. This makes gravity feel less like a force and more like a bookkeeping effect. Objects move along geodesics because those paths preserve certain informational structures. Falling is not being pulled. It is following the grain of emergent space. Now pause and let that settle. It is a radical reorientation, but one forced upon us by consistency. Black holes are not optional features of the universe. They are unavoidable predictions. And once they exist, they demand reinterpretation of our foundations. We often ask whether black holes destroy information. The deeper question may be whether they force us to redefine what information is. Is it something localized or something relational? Is it something an observer can always access or something that exists independently of access? Black holes suggest the latter. Information may exist without being retrievable by any single observer. That challenges a deeply held intuition, but not a logical principle. Nature is not obligated to make everything knowable. And so we find ourselves at a quiet impasse. Black holes sit at the intersection of what we can describe and what we can only infer. They mock simple pictures while rewarding careful thought. They refuse to be reduced objects, yet insist on being taken seriously. As we continue to probe them, we are really probing the limits of explanation itself. How far can concepts like space, time, and causality be stretched before they dissolve? And what replaces them when they do? Those questions remain open. But one thing is already clear. Black holes are not merely endpoints of collapse. They are signposts pointing beyond space-time toward a deeper framework where geometry, information, and observation are woven together in ways we are only beginning to glimpse. And as we follow those signposts further, we may discover that the most profound role of black holes is not to hide answers behind horizons, but to reveal slowly and reluctantly that the questions we have been asking were framed within assumptions that no longer hold. Assumptions about locality, continuity, and even existence itself. Assumptions that begin to loosen their grip the moment we seriously entertain the possibility that spacetime is not the stage of reality, but a provisional map drawn by underlying rules whose full structure is still waiting just beyond the edge of our current understanding, where the next step forward will require us to rethink not only what black holes are, but what it even means for something to be real when the familiar language of inside and outside, before and after, observer and observed, is no longer sufficient to capture what is actually going on beneath the surface of the universe as we experience it. And that realization naturally pulls us toward the next layer of the mystery, where the question is no longer about black holes alone, but about how any consistent universe could give rise to observers capable of asking these questions at all, within a framework that may itself be emergent, fragile, and far stranger than the calm continuity of spacetime has ever led us to believe, because once you reach that point, you can no longer avoid wondering whether consciousness, observation, and information are fours, a start of the same structure that gives rise to horizons and geometry, and whether the story of black holes is quietly pointing us toward a deeper connection that we have not yet learned how to articulate in the language of physics as we know it, but which nonetheless seems to be waiting there, just beyond the conceptual horizon we are now approaching.